Hey guys, it's Mrs. Holmgren, and today we're going to be discussing section 3.3 and 3.5. It's called Beyond Alkanes. What you should have out is your notes, and we're going to review some material first, and then we're going to go ahead and proceed through your notes. Go ahead and take a look at this cover slide here. So far we've been talking about alkanes, and alkanes are hydrocarbons that have all single bonds. If you take a look here at ethane, the two carbons have a single bond. We have a single bond here, another single bond, and then we have single bonds down here as well between our carbons. So that's what makes something an alkane. Alkanes have all single bonds between the carbon atoms. And then if we also take a look here, we have, in this one, we have two carbon atoms, so the prefix for two is eth, and then the ending here is ane because of that single bond. That's an alkane. Three carbons in this one, we've got a prefix of prop, and then we have four carbon atoms here with the prefix of bute, all ending in ane. So that should be review material from your alkane chapter. So in the previous slide, we took a look at the prefixes meth for one carbon, eth for two carbons, prop for three carbons, and bute for four carbons. In this PowerPoint, we're going to be talking about alkenes and alkynes and some modifications that can happen to those hydrocarbons. So it's important that we review the rest of these prefixes. I'd like you to take a second and think about those prefixes and fill them out in your notes, and then I'll go over them. Okay, so we did meth, eth, prop, bute here, so we still need to go over 5, 6, 7, 8, 9, and 10, and hopefully you came up with pent, hex, hept, oct, non, and dec. And then saturated versus unsaturated should also be reviewed. Alkanes are saturated hydrocarbons because they have all single bonds, allowing the maximum number of hydrogen atoms to be attached to the carbon atoms. Unsaturated hydrocarbons are your alkenes and your alkynes, because as soon as you add that double bond and that triple bond, you start to lose some of the hydrogen. Talk a little bit more about saturation. Again, you should be following along in your notes and filling these things in. Alkanes are saturated, as I already said. Each carbon atom is bonded to four other atoms, all single bonds. And so if we take a look at that ethane, there's my carbons, and again, they would all have four bonds, bonded to four other atoms. So this carbon right here, this carbon guy right here, he is 1, 2, 3, 4, bonded to four different atoms. And now this carbon is bonded to 1, 2, 3, 4 different atoms. What do we use alkanes for? Hopefully you remember this from last section. Your Petroleum B chapter was all about alkanes, and alkanes are primarily used for burning. We can calculate the number of calories per mole. We can calculate calories per gram of a hydrocarbon when it burns. Mostly the alkanes, when we talk about methane, they're decane. Those are a lot of our burning hydrocarbons. Alkenes are unsaturated. What happens here is the carbon that always forms four bonds, two of those bonds end up double bonding to another carbon. And so we end up then with only 2 hydrogen rather than 3 hydrogen on each one of these carbons. And that makes the molecule unsaturated because it's no longer saturated with hydrogen, because this double bond caused a loss of the hydrogen when this bond formed. And we changed the ending to ene. Our prefixes remain the same, meth, eth, prop, prop, but, pent, hex, hept, oct, non, dec, but the ending changes. So here's an example of ethene. This is the one I just drew on the previous slide. Notice that we still have 4 bonds, 1 bond, 2 bonds, 3 bonds, 4 bonds. Our prefix is eth for the 2 carbon atoms that we have, but the ending changes to ene, and we lost a hydrogen. Double bonds, we share 4 electrons at the double bond. This is review material. Chemically, the double bond is more reactive, and then it resists rotation around itself. So if I have these carbon atoms that are double bonded together, you saw this in the model building lab that you had, the molecule can't twist around. And so this is where we end up with those cis and trans isomers that you talked about in our first petroleum chapter, and those are going to come up again in this. Alkenes are typically builders. And as we've already said, this petroleum C chapter is about building molecules. So what are we going to, other than burning, what are we going to do with these alkenes? Well, we are going to make plastics. We're going to make synthetic fabrics like nylon. We're going to make synthetic rubber. We can make adhesives, pesticides, pharmaceutical products. Basically, if you're not burning the petroleum, an alkene or an alkyne. So alkynes then, alkynes have that triple bond. So here's my carbon. It's going to be triple bonded to another carbon, and that leaves for only 1 extra bond with hydrogen. So this is 2 carbons here. 2 carbons then would be the prefix of eth. The triple bond then tells me that the ending is going to be ine. And so we have 6 electrons being shared at the triple bond. And again, this thing. So this is ethine. Oop, this guy's a little off center. This is the same drawing that I just made on the previous slide. We've got a single triple bond holding those carbon atoms together. Now we move on to another group of builder molecules other than alkenes and alkynes. These are called cycloalkanes. And so this prefix cyclo tells the reader that we're making a ring. We're talking about carbons that are going to loop back and be bonded to themselves. The general formula for a cycloalkane is CnH2n, which is the exact same formula as an alkane, because when you loop the carbon back to itself, you lose hydrogens when that loop reforms. So I'm talking about taking carbons and looping them one to another, always having 4 bonds, just like we always have. These would be hydrogens that are stuck on here. I don't know why I drew that one off to the side first, but I did. Okay, so we end up with these geometric shapes, basically. So if I were to shorthand draw this molecule that I just made, you can simply draw a square, and each corner of the square is going to represent one of those carbons, and it's understood then that you would have the hydrogen attached to it. So you can just draw these as geometric. So here we have, oh my, this molecule did not transfer to this program very well. So let me draw this off to the side. Okay. So I can just draw this molecule as a 1, 2, 3, 4, 5, 6. This is a hexagon, right? And so at each one of these corners, I have a carbon atom that's understood that it's going to have 2 hydrogen attached to it. So let me draw these bonds in for my hydrogen. And so because it's a looped structure, I'm going to use that prefix cyclo. There are 6 carbons, so hex, and they're all single bonded ane. So this is cyclohexane, and this is a starter material for making nylon. Here are some other cycloalkanes. Again, at each point we have a carbon. Okay, so those are my 3 carbons. Cyclo, it's a loop, which is a triangle here. 3 carbons, prop, and they're all single bonded ane. Again, my next one, cyclo, it's a loop of carbons, 8 carbons, oct, and then my ending would be ane because they're all single bonded. So this is cyclopropane and cyclooctane. Okay, moving on to some more builder molecules. These are called aromatics. Aromatics are a ring, so they're a cyclo. But what's different here is that we're going to add a double bond. And so the double bond is going to rotate, alternate around the ring. Most of these are what we use to create smells or flavors in foods. And so the pine fragrance that you would have in your car air freshener is an aromatic compound. Wintergreen that you get in gum or mints, that's an aromatic compound. These are all hydrocarbons. Another one is banana flavor, strawberry flavor. Lots of the mints are aromatic compounds that we make in a lab and then we put. So here's our simplest aromatic compound. This is called benzene. This is a benzene ring. If I were to just draw this as a geometric shape, we put in these alternating double bonds, and that we can use to represent benzene. And these electrons that are being shared in the bond, they don't just stay in one place. They're going to be shared all around this entire molecule. So the best way to actually represent benzene is by drawing your hexagon for the 6 carbons, and then we actually draw a circle in the middle. And so that circle is representing that those electrons are being shared throughout the entire molecule. So here's benzene. Here's the shorthand version that I just drew. This is describing that those electrons are actually shared around the entire ring between all of those carbons. And so we would have, the hydrogens would be sticking off of this molecule, just like you would see in a regular molecule. The carbon always has to have 4 bonds. So whether they're double bonds, triple bonds, single bonds, whether they're adding hydrogen, carbon must always have 4 bonds. Aromatics are naturally found in petroleum. We can remove those aromatic compounds by distillation, and we can make aromatic compounds by fractioning some of those hydrocarbons and cracking hydrocarbons. You've learned about catalysts, so we can add catalysts to crack hydrocarbons and turn them into compounds. Aromatics can be used to raise octane ratings, so in this case an aromatic would be used to be burned in your gas tank. The focus of this is that we're going to use aromatics for building molecules. So now we're just going to go through a list of substances that contain aromatics molecules. So polystyrene is one. Polystyrene is a polymer. So this is the monomer that we would link. So here's an empty bond here and an empty bond here. So this entire monomer would get repeated to the right, it would get repeated to the left over and over and over and over again. And then here we have that benzene ring that's attached to the monomer. So the monomer is going to link one to another, one to another, one to another, one to another to make a polymer. And polystyrene is what we have, it's styrofoam basically. And so if you have one of these styrofoam bowls or one of these to-go containers, it's basically one molecule that's just linked one to another, one to another. And so this is a builder molecule that contains an aromatic compound. Our next one is TNT, trinitrotoluene. Trinitrotoluene is an explosive. You can see right here in the middle is our benzene ring, our aromatic compound. Then trinitro, here we've got nitrate, nitrate, nitrate. Okay, so trinitrotoluene is where that comes from. And again, here we've got a bond where we can link these together. The problem with benzene is a possible carcinogen. Benzene will cause leukemia. So any substance, any polymer that contains benzene isn't really the best thing for you to be eating off of. It's not the best thing to burn and inhale. Let's avoid that. So here we have a slide that shows you all of the aromatic compounds that can be found in cigarette smoke. These are all substances that are found in cigarette smoke. But here we have a benzene ring. Benzene itself is found. Can you say benzene ring when you look at this one? Naphthalene, which is what makes up mothballs. So there's that ingredient that gives mothballs its smell is in cigarette smoke. So you've got cancer-causing agents, benzene rings that are in cigarette smoke. And then without the benzene rings, we also have formaldehyde that's being burned, hydrogen cyanide that's being burned. So there's my anti-smoking. Lastly, as we get to the end of these notes, what I want to point out here is, in addition to our, alkenes and our alkynes, and then we talked about our ring compounds, and then we talked about rings that are aromatic, we can also add elements to hydrocarbons, and we call these derivatives. And so all of these so far have just been hydrogen and carbon. They're hydrocarbons. But we can continue to make even more builder molecules by adding other elements like oxygen, nitrogen, chlorine, and sulfur. In our note of notes, we are going to be talking about a group of derivatives that just contain oxygen. And so alcohols, ethers, esters, and carboxylic acids are these huge groups of substances, other builder molecules that contain oxygen. And we'll take a look at those in section C6 in our notes. So that is the end of C3 and C5, where we talk about the basics of builder molecules. Thanks for listening, and hopefully you got your notes filled out.